Hola chicos y chicas, soy Nicolás y vamos a hablar sobre las fórmulas de Vietas. No, I'm not going to do the whole video in Spanish. I wanted to talk about Vieta's formulas with you all. They deal with how the coefficients of a polynomial affect the roots, the zeros, the solutions of that same polynomial. And to start off our conversation, let's consider the equation x squared plus bx plus c. And let's let the roots be a and b, which implies that x minus a times x minus b are factors by the factor theorem. So let's multiply x minus a times x minus b together. We get x squared minus bx minus ax plus ab, or x squared minus b plus a x plus ab. That is a pretty cool result there. So what does that result tell you? That result tells you that if you have a monic polynomial, meaning the leading coefficient is 1, then the sum of the roots of that polynomial, is given by the negative of your second coefficient here, your b. For example, x squared plus 3x plus 2 factors into x plus 2 times x plus 1. So its roots are x is equal to negative 2 and negative 1. So the sum of its roots is negative 3. Now, but realize, look at this. From what we just did right here, for a quadratic, the sum of a quadratic's roots is always the negative of your second coefficient here, your b, and the negative of 3 is negative 3. Now, this AB here is the product of the roots, right? A and B are the roots. AB is the product of the roots. And here we found that the roots are negative 2 and negative 1, and the product of those numbers is 2. Negative 2 times negative 1 is 2. But look at this. This also tells you that the products of the roots of this polynomial are also 2 right away, right from the start. So Vieta's formulas attempt to generalize this result here. And by the way, this is true for any quadratic, and they'll kind of like to ask you quadratics on mu tests, where the sum of the roots is the negative of the second coefficient and the product of the roots, this is your second coefficient, and the product of the roots is just your third coefficient here. And if you don't remember that or have trouble believing me, I mean, FOIL it out for yourself and see. Now, let's do, one other thing I should mention. So, let's say that we are given a quadratic that isn't 1. For example, if I gave you 6, if I gave you 6x, if I gave you 6x squared plus 3x plus 2, for example, this is not a monic polynomial because its leading coefficient is 6, not 1. So let's say I defined f of x to be that polynomial. So what basically you do is you just divide that 6 out of the polynomial. So let's define g of x to be equal to f of x over 6, which in turn is also equal to x squared plus 1/2 x plus 1/3. In other words, I just divided by 6 divide by 6, divide by 6. Okay. Now the roots of this here are the same as the roots of this. And also, if we're considering roots, we're setting this equal to 0. We're setting this equal to 0. And since f of x equals 0, and g of x is equal to f of x over 6, then g of x is also 0. So the sum of the roots of g of x is still just for g of x, the sum of the roots is just negative a half. You just took the negative of this. And your product of your roots is still a third. And if you don't believe me on that, use the quadratic formula, use whatever it is that you would like to use, and you will get that result. So in other words, if you have a leading coefficient, just divide it out. Since you're setting these things equal to 0, this new polynomial divided will still be equal to 0, so they'll still have the same roots, and you can just look at the coefficients just as if you had a monic polynomial after you divide out the leading coefficient so that it's 1. Okay, now let's consider the cubic case. This might bore you slightly because I am going to FOIL it all out, but I want to just show you what it would look like for a cubic. So, we start with a polynomial f of x, and we let its three roots be a, b, and c. So therefore its factors are x minus a, x minus b, x minus c. And we're going to multiply this out like how I did up here, and we're going to see what that leads to. So let's just focus on this first two here. Also, I'm not going to group anything until I've done all the multiplication. So foiling out here, AB, that's an AB. Now we're going to multiply that whole thing by x minus c. We're going to get x cubed minus, I hope I don't make an algebra mistake, minus x squared b. This is a plus bcx minus x squared a plus, and if you want to skip through this, I wouldn't really blame you. Plus abx minus abc. Okay, so this is it all foiled out here. Now we're going to do some grouping, so we get x cubed still, minus, now I'm going to mess with this and these. I'm going to mess with the x squared terms now. So I'm going to make it negative a plus b plus c x squared. Now I'm going to mess with this, this, and this. I'm going to make that plus ab plus bc plus cax minus, and then still an abc. So this is basically Vieta's formula for a cubic polynomial. So it tells you it's kind of a similar pattern if you don't already see that. So, but let me break it down. Again, your coefficient of the term, so if I have x cubed plus ax squared plus bx plus c, oh, that's a 6, c. So your sum of your roots of this equation here that I've just written down is negative a by this here. See, a plus b plus c, and then you've got a negative sign. So that coefficient represents the sum of your roots. Now this here they do ask for it sometimes. I usually kind of denote, there's not really a specific way to denote this, but I usually kind of think of it as the pairwise product sum. Pairwise product sum. And I think of it that way because, well, you're summing, first of all, and you're summing pairs of products of A's, B's, and C's. And now notice what you're doing is you're looking for all the possible different ways you can arrange A, B, and C in groups of 2. In other words, if we have A, B, C, and we want to take, if we want to take 2 out of those 3 letters, we want to find the all those different possibilities, we can take the A and the B, we can take the A and then the C, or we can take the B and then the C, if we're just looking to take 2 of them. And so that's what is going to happen here. You're going to have all the product of all the different possible ways you can take 2 out of the 3 roots, and then you're going to sum them. And that's usually known as the pairwise product sum. Sometimes they might just say on a math test, on a mu alpha theta test or something, find this value, and they might just call it that value instead of the pairwise product sum. But just that's what's going on there. And again, so here in a cubic, the product of your roots here is negative C, because you've got A, B, C, and then you've got a negative here. So I'm not going to multiply it out for a polynomial of degree 4, but I am just going to kind of write it here, and I'm going to kind of write it using my intuition. So we have x to the 4th minus, and now we're going to have 4 roots because it's a polynomial of degree 4 by the fundamental theorem of algebra, the corollary to the fundamental theorem of algebra. So this is what it's looking like for a polynomial of degree 4. So our first coefficient is always going to be the negative of the sum of the roots, and I don't know if maybe did it say, I think I erased it, but here I'll just write it over here. We had x squared minus a plus bx plus ab, and we had x cubed minus a plus b plus c x squared plus ab plus bc plus ca x minus abc. So like the signs are alternating. We've got a positive and then a negative and then a positive, and then there's nothing left. And here we got a positive and then a negative and then a positive and then a negative. So the same thing is going to happen here, and that should make sense to you. So we're going to have plus. Now I'm going to take the pairs of these letters. So I've got A, B, C, and D, and I want to find all the different ways I can select 2 out of those 4 letters. I can do that A, B, I can do that, and I'm going to sum these all. I can do A, B, I can do A, C, I can do A, D, I can do B, C, I can do B, D, and I can do C, D. Not like the disc, but A, B, A, C, A, D, B, C, B, D, B, C, D. Sounds like I'm saying Morse code. Yeah, that's it. That's all the possible ways you can select 2 of those 4 letters. And now we have minus, and now what we're gonna do, we're gonna add in something a little different here. We're finding the number of ways we can select 3 out of the 4 letters A, B, C, D, and we're gonna take the negative of it because the signs alternate, and we are going to sum them all up. So I can do A, B, C, I can do A, B, D, plus, I can do B, C, D, C, A, D. Have I done C, A, D? C, A, D. CAD. Can't do CBD, I already have that written down. CDA, that's this. ABC, ABD. Yes. ABC. Yeah, so that's it. Hopefully, I mean, they're usually not going to go up to degree 4, but just realize that that's what I'm doing here. I'm writing down all the different ways I can select 3 out of the 4 letters and then summing them up. And now lastly, the sign's going to alternate, so now it's going to be a plus. And now we're looking for all the ways we can select 4 out of the 4 letters here. That's just A, B, C, D, and that's it, because there's only 4 letters to choose from. So for a polynomial of degree 4, again, the sum of its roots is just the negative of that second coefficient in. If I have x to the 4th plus ax cubed plus bx squared plus cx plus d, this negative a is the sum of your roots. B is this value here, this specific product of the roots A, B, C, and D. Negative C is this value here, the triple-wise product sum of the roots, because you're taking triplets of the letters, you're multiplying them all together, and then you're summing them all up. And then lastly, D is the product of all the roots. And hopefully you can kind of see where this is going. I would ask you to perhaps try and tell it to me for x to the 5th and see what happens there. So just explore it. What else would I like to share with you? Maybe some examples of using this might be nice. Let me find a good example here. So, let's see. I know a good example. I know a good example. Okay, here's a good example. So we want the sum of all possible values of xy if x and y are such that xy minus y squared is equal to 3, comma, xy plus 2x squared is equal to 1. So you're like, how in the world would I use Vieta's formulas for this? So the idea is that we want to force this system of simultaneous equations into a polynomial of some variable, and then from there we can use Vieta's formulas. So how am I going to do that? Just doing some basic arithmetic here. Negative y squared is equal to 3 minus xy, and 2x squared is equal to 1 minus xy. So just negative 2x squared y squared is equal to 3 minus xy times 1 minus xy, just multiplying the equations together. So we get 3 minus 3xy minus xy plus x squared y squared. So this is just negative 4xy. So what do I want to do? I'm going to add the negative 2x squared y squared. So I'm going to get, because I like positive leading coefficients. So I'm going to get 3x squared y squared minus 4xy plus 3 is equal to 0. And that's what we want. We want it to be set equal to 0. Now, realize that this polynomial is a quadratic, I forgot the A, quadratic in xy. In other words, if we were to let u, or whatever variable you want, be equal to xy, we would get a quadratic in the form a u squared plus b u plus c, the usual formula. And if you don't believe me on this, let u be xy. We get 3u squared minus 4u plus 3, which is obviously a quadratic, right? That's the form you're used to. Here, the quadratic is just in terms of xy instead of a single variable. Now, also remember that in this problem, I never assumed x or y to be an element of the set of real numbers. In other words, x and y can also be complex numbers. So what I'm saying here is that Vieta's formulas, I mean, they are like foolproof. In other words, they like when you're looking for the product of the roots, it's telling you the product of all the roots, including if there's complex ones, those too, so just keep that in mind. It's not just considering the real parts, it's considering everything. Now, we have this polynomial here, but it is not monic. Its leading coefficient is not 1, so let's divide by that leading coefficient to get x squared y squared minus 4 thirds xy plus 3/4 is equal to 0. Now, from here, we're looking for the sum of all possible values of x, y, and we're not assuming that x and y is a real number. X and y are both real numbers. In other words, they can be complex too. So, by Vieta's formulas, that answer is just 4/3. It's the negative of negative 4/3. Because if you remember, the negative of that coefficient that I just circled is the sum of the roots by this formula that I'm circling now, that we in the beginning proved to ourselves. So the sum of all possible values of x, y in that system of equations is 4/3. And the product of all possible values of x, y in this equation is 3/4. Isn't that just so cool? I think that's just really, really something. I mean, that's pretty special. So, that particular question was not actually from U alpha theta. Let's see here. This one is from U alpha theta. I've never done this one before, so let's see how this goes. So, we're saying that the roots x, and by the way, as I'm doing these problems, please pause the video and try to do them on your own. So we have polynomial x squared minus 3x plus 1 with roots at a and b. And the roots of x squared minus mx plus n are at 3a over b and 3b over a. And we want m plus n. Okay. So what do I want to do? What do I want to do? The roots Okay, well, from Vieta's formula on this polynomial, I know that 3 is equal to AB. I'm sorry. 3 is equal to A plus B. The negative of negative 3 is equal to the sum of the roots, and 1 is equal to AB. Okay. And here I know M is equal to 3A over B plus 3B over A, which is 3A squared plus 3B squared over AB. Okay. Interesting. Oh, well, look at that. Oh, okay. Now, AB, we know, is 1. Now, A squared plus B squared, we need to figure that out. Now, we know 3 is equal to AB, and we have an A to the 1 and a B to the 1, so it would hopefully make sense to you to square this equation. And we're going to get some squared term. Oh, not 3 squared is 9. So we're going to square the 3. We're going to square the A plus B. We get 9 is equal to A squared plus B squared plus 2AB. So also AB is 1. So this is just 2. So 7 is equal to A squared plus B squared when we subtract the 2 over. So M is nothing but 3 times A squared plus B squared, which is 3 times 7, or 21. Now, N is equal to 3A. Oh, that's why they made these. Okay, yeah. N is the product of the roots. That A and that A go away, that B and that B go away. We get that N is equal to 9. You have 3 times 3. N is equal to 9. So, the value of M plus N is 30. 21 plus 9. Easy as that. It's as easy as that. Now, it's probably going to just take you some time to get used to using Vieta's formulas, but they are just so cool. They come up in very strange ways sometimes. I'm seeing here. Let's see here. Let me give you one more using Vieta's because I think it would be beneficial. So, let's say I want you to find the constant term. So we want the constant term, in other words, a term without any x or variable. Constant term of a monic, meaning leading coefficient of 1, quartic, meaning of degree 4, or with the highest exponent of 4, polynomial, with rational coefficients, I'm just going to write coef that are an element of the rationals, which, if I remember right, is Q. I think that Q stands for the rationals. With rational coefficients, and has 2 roots. Now, obviously, it has 4 in total, but they're giving us 2. And those 2 roots are 2 minus I, and where I is the square root of negative 1, and 2 plus the square root of 3. So, now, this requires a little bit of background. Realize that, and you should remember this from your algebra class, if you have a polynomial with a root a plus bi, then what this implies is that a minus bi must also be a root. It must also be a root. And a couple ways that we can show this. Well, one way, let's use René Descartes' rule of signs for this. So that's just dealing with roots and sign changes of a quadratic. So let's say okay. I'm just gonna kind of spitball here. Oh, I want to keep that a minus. Okay, so the maximum number of positive. Oh, I want to keep that a -2, -1. The maximum number of positive real roots that this equation can have is the number of sign changes, which is 1. So it's guaranteed 1 positive real root. Now f of negative x, this is f of x. F of negative x is x to the 4th minus 3x cubed minus x squared plus x minus 1. That has 1, 2. It has 2 sign changes, so it can either have 2 or 0 negative real roots. So now realize that it can't have 2 negative roots. The reason why that is because let's say it did have 2, then and the polynomial is guaranteed 1 positive real root. So if it had 2 positive real roots or 2 negative real roots and 1 positive real root, it would have 3 roots. And by the fundamental theorem of algebra, since it's a degree 4 polynomial, it has 4 solutions. So that would leave 1 imaginary root. But if you have 1 imaginary root, that's impossible. If you have an imaginary root, then by the complex conjugate, the conjugate of that imaginary root has to be there as well. So what I'm getting out of all this is that if 2 minus I is a root, then 2 plus I is a root as well. And also, if 2 plus the square root of 3 is a root, then 2 minus the square root of 3 is a root as well. And another way you can think about this is we were given that the coefficients are rational numbers, the ratio of 2 integers. So if we didn't include 2 minus square root 3 as a root, then what would happen is, okay, well, if x plus 2 square root 3 is a root, then x minus 2 plus the square root of 3, or just x minus 2 minus the square root of 3, is a factor. And now if we didn't have the complex, or not the complex, because we're not doing complex numbers right now. If we didn't have the conjugate of 2 plus square root 3, 2 minus square root 3, being a root of that polynomial, then what would happen is that when we FOILed out all of our when we FOILed out all of our factors to get our original quartic polynomial, we would have some variable terms that would have this square root of 3 or some multiple of it as their factors. Now the square root of 3 is not rational, so that would go against this condition here. So that's another reason why this has to be a root, given that this is a root. Likewise, if we multiply 2 minus I by 2 plus I, we ended up getting 4 minus I squared, which is 4. I squared is -1, so we have minus minus -1. 4 plus 1, or 5. So, if we were multiplying by something other than 2 minus I, we would get an imaginary number. And imaginary numbers are not elements of the set of rational numbers, thereby contradicting this condition as well. So that's a number of ways to think about it. Now, the product of the roots, then, is just 2 plus I times 2 minus I times 2 plus square root 3 times 2 minus the square root of 3, which is, now if we take this, we just showed that to be 5, and when we multiply this, we take the square of this number, and we take the square of this number, we subtract them, we get 4 minus 3, which is 1, and 5 times 1 is 5. So the product of the roots is 5. And the constant, okay, the product of the roots is 5. So the constant term of the quartic is 5. Okay, and the reason why it's not a negative 5, if you remember from like those formulas that I written where I wrote like x squared minus a plus b x plus ab, and how the signs alternated, and like for a cubic it ended up being negative abc. The sign on that constant term alternates every degree that you increase. So what you can do to check for that, whether that negative sign is there or not, is you can raise -1 to your degree, or your exponent, your highest exponent term. And if that number is positive, then the constant coefficient is positive, and if it's negative, then the constant coefficient is negative. And -1 to the fourth is 1, so 5 is our answer. And that has come up in mu alpha theta tests, where if you are given 2 plus I as a root, then you have to know that 2 minus I is a root, or if you are given 2 plus square root 3 as a root, then you'd have to realize that 2 minus square root 3 is a root. So just be aware of that. I believe that is all I would like to show you. If, for you all that are still watching, are interested, here is my question to you. My question to you is, I want you to use induction to prove that the kth symmetric sum, in other words, the piecewise product sum, the triple-wise product sum, the quadruple-wise product sum, yada yada yada, is -1 to the k a sub n minus k over a sub n. And on that note, I do believe we're done.